Good afternoon, this is Schweitzer, and this is a short video on basically, are you proficient? Our standard here is 4-1B. This is looking at the internal factors. Basically, why is a solid? And this is, again, all about intermolecular forces, properties of solids, and so forth. So this is doing a really trying to demonstrate how a molecule becomes polar. This is something that is maybe a little bit more prevalent in the bonding chapter. I always say that 3-4 is the same as 4-1B, and it pretty much is. This leans a little more towards states of matter and solids. Either way, so our first question. This question came out in the new this style of question came out in the new AP curriculum probably, I don't know, 2015-ish, somewhere around there, 16. Following the following substance has these properties. It's got a melting point of 3800, is insoluble in water, does not conduct electricity. Which substance is this? Okay, answer here. Alright, so we're looking to weed out a few things here. First things first, high melting point. So this one here, real high melting point, might lead me to think of a network covalent. That's what that's kind of telling me. Maybe ionic, with a real high charge differential, but insoluble in water. Okay, so that might narrow a few things down. I know that NaOH is quite soluble in water. Many ionic compounds are fairly soluble in water. Not all of them, but we'll take that maybe off the table here. Does not conduct electricity. Now, we don't do a ton of stuff on metals, but this would really cross out the idea of a metal. And there are some metals that have extremely high melting points. So, in this case, I would say, okay, it's not tungsten. It's not an ionic compound, so, and looking most likely at carbon in the diene form, mostly because of this high melting point. Next question. Okay. Two chemicals here. The one on the left is called benzene, and the one on the right is called benzoic acid. You can pause the video, take a look at this. Alright. To the left we have a chemical benzene, considered a Class A carcinogen, highly utilized in the chemical industry. To the right we have a chemical benzoic acid. It's one of the most highly utilized chemicals in food preservation and can therefore be eaten without harm. So you might see a label on a food that says sodium benzoate. That's just this chemical minus the H. So it alters the pH and therefore inhibits growth via disruption of energy production by bacteria. So, anyways, what about these things? What's the question saying? Which of these substances which of these substances might you expect? Okay, one, to be a solid. Well, we're looking for a substance that has an increased amount of intermolecular forces. This guy has the ability to hydrogen bond, and it's got a large area here, which could be pretty good at London dispersion forces. And this same thing goes for that guy. This piece here is essentially, it's the same thing. They're not showing hydrogens here, but there is a hydrogen on each end. This is called a benzene group, and that's a benzene group by itself. So this guy just has a little bit more hydrogen bonding. And of course, this is the whole premise of this whole intermolecular attractions, to be able to look at a chemical and explain about what happens. So it's somewhat polarizable because of the London dispersion forces here. And then over here we have an area where we're going to have possible partial negative and a partial positive. All right, so I would say if one's going to be solid, it likely would be, let's say, called, let's go with the acid, the one on the right side. So we'll call this the B, we'll call this A, just for sake of giving it an answer. This one here is B, the acid. Form of hydrogen bonds, as I mentioned, okay, this one is going to be benzoic acid. We'll go BA for the benzoic acid. And benzoic acid, okay. Form LDFs. Now, again, be very careful. Just because the benzoic acid can hydrogen bond doesn't mean it can't form London dispersion forces as well. So this is going to be both. Okay. Dissolved in water. Only one of these chemicals is going to be able to hydrogen bond into water, and that's benzoic acid, the one on the right. Take a moment, read the question. Okay, butter is solid at room temperature, but, do a typo there, but some unsaturated oils are liquid at room temperature. From what you know about intermolecular attractions, which of the following substances might be liquid and why? Alright, so here we know that sometimes we can get liquids here. And in this case we have a end here, and they're both the same. This end is a very polar end, and this thing here is forms a lot of things in terms of biological membranes. Sometimes very healthy for these things, for you to be eating some of these fatty acids. There are even things called essential fatty acids, which your body has to have but can't make, so you must consume in your diet. Anyways, so the main thing that holds these things together is a London dispersion force. So if I draw these fatty acids next to each other, and one of the properties of a London dispersion force is going to be a basically surface area, and this is long chains. So we're looking for something that can form long chains, and the reason why the long chains work so well is because one chain can lie right next to another chain and have essentially a very weak attraction between. But if you have lots of surface area, it's like Velcro. One little hook and velour is not very good. But if you have, that might be off the screen here. So if you have many of these things lying up next to each other, they can really attach to one another because it's a very weak force. But you get lots of them, and they can get very close to each other. The force gets much bigger. Keep in mind Coulomb's law: force is equal to the charge times the charge over the distance squared. If you can get very close to these things, very close together, the actual inherent force gets larger. This one right here with the kink in it is going to cause an issue because they're not going to be able to lie that close to each other, and inherently disrupting the London dispersion forces, and therefore making it likely a liquid. Alright, palmitic acid, another question. Keep in mind, I got a few things here. Read the question. Okay. This is another example. Again, it forms pretty much a carbon copy of the last question. But another example here is a saturated fat, all full of hydrogens, all single bonds. And because it's straight, we're going to have a lot of good London dispersion forces here. And we're going to have some hydrogen bonding at the end. So I might think there's a pretty good chance that we're going to have this thing be a solid, or at least a semi-solid, hence cheese or butters or creams, things of this nature. And that ends 4-1b. Internal factors affecting whether something is a solid, liquid, or gas. This is your chapter piece looking at intermolecular forces. Thank you very much.